Hello! Today I'd like to take a deep look into how the Unitree Go-To quadruped robot manages to move so smoothly, right into the heart of control engineering. Its motion is almost lifelike, isn't it? What kind of technology lies beneath that behavior? From basic feedback control to more sophisticated whole-body optimization techniques, our mission today is to uncover the engineering foundations that allow robots like the Go-To to move the way they do. If you're fascinated by what happens inside robots or the science that supports them, you'll surely enjoy this exploration. So let's begin with our expert. First, the absolute basics, the PID controller. What exactly is it, and why is it used so widely?
Right. PID control stands for Proportional Integral Derivative Control. It's a classic in feedback control theory, part of classical control theory. It's relatively easy to implement, stable, and provides reasonably good response characteristics. That's why you'll find it in everything from home appliances to industrial robots and even aerospace systems. Compared with simple on-off control, PID reduces unnecessary oscillations near the target value, hunting and overshoot, allowing smooth and precise control.
I see. So there are three elements, P, I, and D. What role does each one play?
Well, first is P, the proportional action. This produces a control output proportional to the current deviation from the target, the error. It acts like a spring, pushing the system toward the target. The response is fast, but... Yes, in many systems, it doesn't quite reach the target precisely, leaving what's called steady-state error or offset.
I see.
Next is I, the integral action. This accumulates past errors over time, integrating them, and produces a control output proportional to that accumulated value. Its main purpose is to eliminate the steady-state error that P alone can't remove.
Ah, I see. For example, when a robot arm maintains an angle against gravity.
Exactly. Even when the error is zero, it continues to exert force based on past accumulation, like a holding force.
I see. And the last one, D?
D, the derivative action. This looks at how the error is changing, its rate of change, the derivative, almost predicting the future. It acts like a damper, preventing the system from moving too quickly or suppressing oscillations. This increases stability, which in turn allows you to set higher P gains and speed up the response.
But are there any drawbacks?
Yes, it tends to amplify sensor noise.
So tuning these gains, KP, KI, KD, becomes extremely important. Balancing them seems difficult.
Exactly right. Tuning is often based on empirical rules. If you increase the P gain to speed up response, it becomes unstable. You use D gain to suppress that. If you add too much I gain for precision, the response slows down or becomes unstable, and D gain is sensitive to noise. There are always trade-offs. This isn't just a PID issue, it's a challenge inherent to all control engineering.
For the Go-To, if you increase P gain too much trying to move the legs quickly, the whole robot becomes unstable and could potentially fall. So simple PID alone has its limits, as suggested.
PID works well for simple tasks like maintaining joint angles, but it's conceptually insufficient for dynamic walking.
Why is that again?
Because PID is merely a reactive controller that responds to past and current errors. It has no predictive capability to coordinate the robot's overall movement, like determining how it should move in the next moment. Given these limitations, more advanced control methods with better system understanding become necessary.
I see. So let's move beyond PID. What about transfer functions?
The transfer function GS is one of the main tools in classical control theory. It represents the relationship between a system's input and output in the frequency domain using the Laplace transform, a mathematical operation. What would be complex differential equations in the time domain become simple algebraic equations in the frequency domain. This makes analysis and design of single input, single output systems much easier.
What is a Bode plot?
It's a graphical visualization of frequency response, how a system responds to inputs at various frequencies. For example, looking at the frequency response of a mass spring damper system with force as input and displacement as output. At low frequency inputs, the output amplitude is roughly constant, proportional to the input amplitude, and the phase is nearly the same as the input. As you increase the input frequency toward the resonant frequency, the output amplitude increases and the phase begins to lag. When you go well beyond the resonant frequency, the phase approaches nearly 180 degrees lag, while the amplitude rapidly becomes very small. Bode plots have two parts, gain plots and phase plots, and the frequency axis is usually logarithmic. You can clearly see how gain and phase change as frequency increases.
So what can you see from this?
You can see system stability, gain margin and phase margin, as well as resonant frequency and the limits of response speed, what we call bandwidth.
So it's still useful for looking at subsystems like single leg of the go-to.
But for complex systems, like the entire go-to, transfer functions have limitations too. The biggest weakness is that it's a black box model that only looks at input-output relationships. You can't see the internal states of the system at all. The go-to has many internal states, positions and velocities of over 12 joints, body posture and velocity, but transfer functions can't represent these.
I see. So that's where the transition to modern control theory becomes necessary.
That's the flow.
Now this gets really interesting. What's so different between transfer functions and state space representation?
State space representation explicitly deals with the system's internal states. This is the foundation of modern control theory. The system is described by first-order coupled differential equations, the state equation x dot equals ax plus bu, and the output equation y equals cx plus du. What's crucial here is the state vector x. This is the complete internal state of the system at a given time. For example, all joint angles and angular velocities bundled together. It's a glass box model that explicitly models the internals. You can see inside the box.
You can see inside. That's a big difference. What specific advantages does this have for the go-to?
First, it handles multi-input, multi-output systems very naturally and concisely. Systems like the Go-To with over 12 inputs and many outputs. Also, it's easier to apply to cases with non-zero initial conditions or nonlinear systems. But most importantly, you can design controllers that act directly on the system's internal states.
Directly on internal states?
Yes, for example, if a specific joint's angular velocity is too high and wastes energy, you can penalize that to suppress the motion. Or you can limit the body's angular momentum to maintain stability. This kind of precise control based on internal states becomes possible. This was impossible within the transfer function framework. Furthermore, by analyzing the matrices A, B, C, D, you can consistently derive all system characteristics, stability, response characteristics, frequency characteristics. The design and analysis process is strengthened.
I see. Because you can handle internal states, the path to more advanced control opens up. And related to these internal states, we have the terms controllability and observability. What do these mean?
Yes, these are fundamental and important properties in modern control. First, controllability. This is the property of whether you can use the control input U, that is the motors, to move the system from any arbitrary initial state to any target state in finite time.
So whether you can move the robot as you intend with the motors.
Simply put, yes. It's the question of whether the motors can take the robot to any physically reachable state. If the system isn't controllable, no matter how hard you try with feedback control, there will exist motion patterns you cannot control, and you cannot stabilize them. This becomes a prerequisite for stabilization and pole placement, which we'll discuss later. Lack of controllability might indicate that actuators, motors, are broken, lack sufficient power, or are poorly positioned.
I see. So what about observability?
Observability is the property of whether you can uniquely determine the complete internal state X by observing only the system output, Y, values measurable by sensors for a finite time.
Whether you can know all the internal states just from sensor information.
Yes, it corresponds to the question of whether you can determine all joints and body velocities accurately from just IMU and joint encoder data. Since you can't directly measure all internal states with sensors, this becomes a necessary condition for constructing a state estimator called an observer to estimate unknown states from observable outputs. Lack of observability also suggests insufficient or poorly positioned sensors.
I see. So these aren't just mathematical concepts, they relate to physical design and hardware too.
Exactly right. They're powerful diagnostic tools linking control theory and hardware design. Also, these are considered dual concepts. Controllability relates to the influence from input to state, and observability relates to inferring state from output. For a fully autonomous system like the Go2, both are absolutely essential. It must be able to firmly estimate its current state, observability, and effectively act to achieve goals based on that estimate, controllability.
I understand clearly now. So once you know a system is controllable, what can you actually do?
If a system is controllable, you can use a technique called state feedback. This is a method where you determine the control input U as a linear function of the state vector x. That is, U equals minus kx. K is called the feedback gain matrix. Using this, the closed-loop system, the system after closing the control loop takes the form x dot equals a minus bkx. The dynamic behavior of this system is completely determined by the eigenvalues of the matrix a minus bk. These eigenvalues are called the system's poles.
The position of these poles is important?
Critically important. The system's response is directly determined by where the poles are in the complex plane. The more negative and larger the real part, the faster the response converges and the more stable it is. If there's an imaginary part, the response oscillates. The further from the real axis, the higher the oscillation frequency.
I see.
And pole placement is a design technique where you cleverly choose the feedback gain matrix K to literally place the poles of this closed-loop system at desired locations in the complex plane. This allows you to achieve desired responses, like settling quickly or minimizing overshoot.
And the condition for being able to do pole placement is the controllability we discussed earlier.
Theoretically, yes. But there are practical challenges with pole placement.
What kind of challenges?
Even with the intention of making it fast and smooth, directly determining the optimal pole coordinates to achieve that is extremely difficult.
You'd have to decide intuitively, wouldn't you?
Bridging this gap between intuitive intent and mathematical coordinates is what the optimal regulator, LQR, does.
The optimal regulator. What is it?
The optimal regulator finds the optimal gain K that minimizes a cost function J instead of pole coordinates.
I see the letters Q and R.
Q and R are weights, penalties, that the designer chooses. XTQX is a penalty on state deviation. The larger Q is, the more you prioritize performance. UTRU is a penalty on input energy. The larger R is, the more you prioritize energy savings.
So you decide whether to prioritize performance or energy savings through the balance of Q and R.
Exactly. Being able to design with intuitive indicators like weights rather than coordinates is the advantage of LQR.
Let's see this in simulation. First, we'll increase the position penalty Q11. This setting prioritizes position.
As Q11 increases, the poles moved to the left side of the S-plane, and the response became faster.
Next, we'll increase the velocity penalty Q22. This setting suppresses oscillation.
The poles moved closer to the real axis. The response also became smoother with no overshoot.
Finally, let's increase the input penalty, R, prioritizing energy savings.
Now the poles move back to the right towards the origin. The response also becomes quite slow.
Yes, it suppresses control input.
So LQR is a method where, just by adjusting the intuitive weights Q and R, the optimal pole placement is automatically calculated behind the scenes, achieving the desired response.